In this module, we're going to look at how to calculate energy bands for electrons in solids using a technique called the linear combination of atomic orbitals method. Or LCAO theory. So let's start by reminding ourselves of the energy levels in the H2 molecule, because we're going to then extend that to the case of an infinite solid. So in the H2 molecule, we look at the energy starting from two hydrogen atoms, each with a 1s atomic orbital, and bring those atoms together to form the H2 molecule, then we know that one molecular orbital, the bonding molecular orbital, is formed at lower energy than the energy of the isolated 1s atomic orbital, and one molecular orbital is formed at higher energy. And the bonding orbital consists of the two atomic orbitals with the same phase as each other. So I'll draw these both with a plus sign to indicate that both of these 1s atomic orbitals have the same phase, whereas the antibonding molecular orbital is the linear combination of the two atomic orbitals with the opposite phase. So mathematically, you can write that as the bonding orbital is the linear combination of the atomic orbitals with the same phase. We'll put in 1/√2 for normalization. And the antibonding orbital is the linear combination of the atomic orbitals with opposite phase, opposite sign. And we rationalize this by saying, okay, in the case of the bonding orbital, we have a buildup of electron density between the positively charged nuclei, which is favorable and lowers the energy of the system. Whereas in the case of the antibonding orbital, we have a node, the electron density goes to 0, and it's not favorable for bonding. So that we're familiar with from our introductory chemistry classes. Now we're going to extend this to the case of an infinite periodic solid. So we'll now look at a chain of 1s orbitals, or if you like, an HN molecule, an infinite number of hydrogens, all in one-dimensional chain. And we can extend or extrapolate the arguments we just made for the H2 molecule and say that, okay, the lowest energy linear combination of atomic orbitals, just using our intuition, will have all of the s orbitals in phase with each other. So all of these will have the same phase. Just like in the case of the hydrogen atom. So we can write our bonding molecular orbital as some coefficient for normalization times the linear combination of all of the atomic orbitals in phase with each other. And the highest energy linear combination of atomic orbitals, again by analogy with the H2 molecule, will have the 1s orbitals on the adjacent atoms out of phase with each other, so that in between each atomic orbital, again, we have a node. We don't have an electron density contributing to bond formation. And so our antibonding, our most antibonding molecular orbital, most antibonding linear combination of atomic orbitals has the adjacent atomic orbitals out of phase with each other. So far we've just used our intuition, and we've already made quite some progress into thinking about the energy levels of the electrons in this solid. We already can write down the wave function for the lowest energy and the highest energy. But of course, we'd also like to know what the energies in between those limits are. So let's rewrite our wave function in the general case as some coefficient times the wave function for the orbital on atom 1. So let's say we label our orbitals and say they're separated by some distance a, and the first one may be the orbital at x is equal to a, and the second one would then be the atomic orbital at x is equal to 2a, and so on. Or we can be more concise and write this as the sum over n times c sub n phi sub n. So this is a general wave function made from a linear combination of the atomic orbitals. What we know already is that for the lowest energy case, c sub 1 is equal to c sub 2 is equal to c sub 3 is equal to c sub 4. For the lowest energy, and c sub 1 is equal to minus c sub 2, which is equal to c sub 3, which is equal to minus c sub 4, and so on for the highest energy case. And if we want to be even more general, then we can say, we can write this sum over n of c sub n times phi sub n with the specifications on the c's. We can write it as the sum over n times e to the I k times x sub n phi sub n, where x sub n is the position of the nth atom, which is just n times a, and k is what we call the wave vector, which is 2 pi over the wavelength. And once we write our wave function in that form, then in order to meet this description of the coefficients, we see that k is equal to 0 for the lowest energy case, because when k is equal to 0, then e to the I k times x sub n is always equal to 1, and so our coefficients in front of the wave functions are always identical, and k is equal to pi by a for the highest energy case. Because when k is equal to pi over a, e to the I k x sub n alternates as n changes by 1. So at the moment, this may not seem like a very helpful way of writing a sum of 1s and minus 1s, but we'll see soon that this is actually going to be a very useful way of representing the wave function. I want to point out one more fact before we move on, which is when k is equal to 0, then this is equivalent to the wavelength lambda being equal to infinity. And what this tells us is that as we move from one unit cell to the next, there's no change in the coefficient. If the wavelength of the variation from one atom to the next is infinite, then it takes an infinite number of atoms for anything to change, and so there's no change. All the unit cells are the same. So when k is equal to 0, this means the wavelength lambda is equal to infinity, and all of the atoms are the same. When k is equal to pi over a, then in this case, the wavelength lambda, which is 2 pi over k, is equal to 2a, and that tells us that the wave function is identical after translation of 2a. Okay, so soon we'll hopefully see why we might want to write our wave function, which is sum of coefficients times the atomic orbitals, in this slightly more complicated form. Okay, but from our intuition from the H2 molecule, we convince ourselves that we have an appropriate form for the lowest energy orbital, in which the phase between each adjacent atom, each adjacent wave function is identical, and the wave function for the highest energy form, in which the wave functions on adjacent atoms change phase, they alternate sign. Now we want to find a general form for the wave function in between these two limits. And we're going to use the fact that all of the properties of any periodic solid must have the same symmetry as the solid. And so, for example, if the atoms repeat periodically with periodicity A, then the electron density must also repeat periodically with periodicity A. So this is the specific property that we're going to use. The atoms repeat periodically with periodicity A, which we saw in our one-dimensional chain, that was the case. Then the electron density must also. And mathematically, we can write that down as rho of x, the electron density at point x, is equal to rho of x plus a, which is equal to rho of x plus 2a, and so on. But of course, we know that the electron density rho of x is equal to the square modulus of the wave function. It's equal to psi star of x times psi of x. Sorry, it's the square of the wave function, complex conjugate of the wave function times the wave function. And so this requirement that the electron density has to repeat periodically can only be achieved for wave functions of the form psi x plus a is equal to some quantity we'll call mu, we'll write down what that is at the moment, times psi of x, psi of x plus 2a is equal to mu squared times psi of x, and so on, down to psi of x plus, let's write down the general case, na is equal to mu to the n times psi of x, where mu star times mu is equal to 1. The periodicity in the electron density, that rho of x is equal to rho of x plus a, which is equal to rho of x plus 2a, and so on. The equivalent in the wave function is that psi of x plus a is equal to mu times psi of x, where mu star times mu is equal to 1. And this property of mu star times mu is equal to 1 is satisfied by mu is equal to e to the I k for any value of k. And so now maybe it's a little more obvious why we wrote our wave function in terms of sums over exponents rather than just sums over more straightforward coefficients, because what we've just seen is that such a coefficient satisfies the requirement of that the properties of the solid have the same symmetry as the periodicity of the atoms. So let's write that down formally. A general wave function can be written as some general form e to the I k a times phi 1 plus e to the I k 2a times phi 2 plus e to the I k 3a times phi 3, and so on, or sum over n e to the I k x sub n times phi sub n, just as we had before. And such a wave function is called a block function. And we know from our just intuitive discussion by analogy with the H2 molecule that K ranges from 0, which was the lowest energy case, to plus or minus pi over A for the highest energy case. Okay, very good. So we have a general form of the wave function for a periodic solid that's made by linear combinations of atomic orbitals. We looked at an example in one dimension, but this can be generalized to 3 dimensions, and often we'll see the block function written in the more general form that the wave function for a particular k value is a function of position, which can be 3-dimensional, is e to the I k dot r times quantity, it's usually written as u sub k of r, which is called the cell function and this represents the atoms or ions in the unit cell that give the periodicity of the lattice. And in our case, in our example, we had only one atom per unit cell. It's just the 1s orbital on each atomic site. Good, so when we talk about the band structure, what we mean is the energy of these atomic orbitals. So what we'll do next is work out the energies. And in particular, we want to know what the energies of these orbitals, these linear combination of atomic orbitals, are as a function of their k value. Remember, k is equal to 0 is the lowest energy, k is equal to plus or minus pi over a is the highest energy. And this will give us the energies of the atomic orbitals as a function of the k value, is what we call the band structure. The energy as a function of k. Okay, so let's work out this band structure for our orbitals that are made from the linear combination of atomic orbitals. And to do that, we'll write down our usual expression for the expectation value of the energy, which is that it's the integral of psi star times h times psi. Let's stick with our one-dimensional example just for simplicity. And if we didn't normalize, we have to divide by the integral of psi star psi. dx. And in the particular case we're interested in the energy at a particular k value. And so we'll integrate the wave function of that k value times a Hamiltonian times the wave function of that k value, normalize for the wave function of that k value. And our form of our k value, of our wave function, psi sub k, we just argued, is the sum over n is equal to 1. In principle, we'll sum to infinity, but let's just sum to some large number n to keep the mathematics more straightforward. E to the ik n times a is the position of the atomic orbital times phi sub n. So substituting for this form for psi sub k in our E sub k expression, let's write down psi sub k star h times psi sub k integrated over all x. And I'm going to use different indices for the left hand and right hand psi sub k's, just so we don't get too lost. And we'll sum over n is equal to 1 to n for the right hand one, and m is equal to 1 to n for the left hand one. So we have e to the I nka minus mka, where the minus is because of the complex conjugation of the sum over n states, times the integral of the atomic orbital on site n times h, the Hamiltonian operator, times the atomic orbital on site n dx. And in principle, one could calculate these integrals explicitly, maybe if one had the functional forms for these atomic orbitals. The approximation that's usually made is that this integral is set to one value, which we call h11, or sometimes alpha, if m is equal to n. If this is the integral for the 1s orbital on the same atom with itself, then it's set just equal to the energy of that atomic orbital, which we call alpha or h11. It's set to another value, which we call h12, or often it's called beta, if m and n are nearest neighbors. So for example, between atoms 1 and 2, atoms 2 and 3, and so on. And is set equal to 0 otherwise. So this integral between more distant pairs of atoms is set to be 0. And these assumptions, of course, one doesn't have to make them, but they're rather good assumptions because only the atoms that are close to each other are interacting with each other strongly. These are called the tight binding approximation. They're the usual assumptions made in the tight binding approximation. A linear combination of atomic orbitals theory. Okay, so if we work out, then with these assumptions, we work out this summation, then in the double summation, n is equal to m happens n times, capital N times, so we get n times alpha. Let me write this down. So then with these approximations, the integral of psi k star h psi k dx is equal to n times alpha, because in the double sum, little n equal to m happens capital N times, so we get n times alpha. Little n is equal to m minus 1 also happens n times, so we have n times e to the I m minus 1 minus m ka, which is e to the minus I ka times beta. And then little n is equal to m plus 1, also happens n times. So we have n times e to the I m plus 1 minus 1, which is e to the plus I ka, also times beta. So you can convince yourselves that we got the right numbers of right counting in the summations here. We can simplify this to n times alpha plus 2 beta cosine ka. So that's the numerator. The denominator, the integral of psi k star psi k dx is equal to some little n is equal to 1 to n, little m is equal to 1 to n, e to the I n minus m ka, the integral of phi m star phi n dx. And this integral is equal to 1 if n is equal to m, or is equal to 0 otherwise. And so this integral reduces just to n. And so our energy, which is the ratio of capital N alpha plus 2 beta cosine ka and capital N, then is just alpha plus 2 beta cosine k times A. And remember that, so this is our band structure, our energy is a function of k. Remember that cosine ka ranges from +1 to -1. And so the bandwidth, the range of energy values over the given range of k is equal to 4 times beta. So let's finish by sketching our energy level diagram then for our one-dimensional chain of s orbitals. So here's the energy as a function of k, and we know that k ranges from 0 to plus and minus pi by a, and our energy is at its maximum value at plus or minus pi by a, and its minimum value at k is equal to 0. And the range of energy values is 4 beta. So let's mark the value of alpha here. And so at k is equal to 0, we're 2 beta lower in energy than alpha. And at k is equal to pi by a, we're 2 beta higher in energy than alpha. And in between our energy versus k, our dispersion the energy levels as a cosine form. And this should be symmetrical left and right of the energy axis. Sorry, it's not very well drawn. The other thing we know is that the wave function down here has all of the atomic orbitals in phase with each other. Each unit cell is identical, and the wave function at plus or minus pi over a has the adjacent atomic orbitals exactly out of phase with each other. Their signs are alternating, and that's the highest energy linear combination of atomic orbitals. There's a node between every atom. And in between, there's a gradual evolution from there being 0 nodes between the atoms to there being a node in between every atom as the K value increases from 0 to pi over a. So that's it for today, and thanks for listening.